Great, thanks, Rivia. So just in terms of a brief agenda for today, so as I said, this is going to be a two-part series. And what we've decided to do in this first session is it's really focused on the basics and getting up to speed and how you can install Python, PyPSA, the library itself. We're going to work through a small worked example that just shows some of the basics of how you would set up a network in PyPSA and how you would solve that. And then that's something that you can start to play around with some of the more complicated worked examples within the PyPSA library set. And then we're going to move on to sort of the first, what I'd say, building block of the bigger PyPSA-RSA model. And that's really the set of scripts that we use to do solar and wind resource mapping across different regions of the country. So today, for people who are a little bit more advanced users of PyPSA, I think you might find it a little bit on the basic side. But next week, we'll be diving into a lot more technical detail around the PyPSA-RSA model itself and some of the basically how to use that, and that will be a bit more of an advanced session. So we're going to try to keep this as interactive as possible. So I think we will pause and take questions and discussions as we go along. We will be recording this session, so basically we will make this resource available on our website, so you can go back in time, and when you start working through doing all the installation and everything, then you can have this as a resource. But within this session, we're not going to have time to kind of help everyone install everything. But we are available if you get stuck on any point in the future. So just a brief introduction to who we are as Meridian Economics. So we are a specialized energy and climate economics consultancy, and we do a lot of work at this kind of intersection between economics, the energy space in South Africa, finance, and climate change. We have a sort of dual role that we work in. So we do a lot of commercial advisory services for everyone ranging from kind of on the demand side and large industrial customers, helping them try to figure out the energy transition through to IPPs. And then we do a sort of more of a think tank role, which is kind of what supports a lot of this open energy modeling. And that's focused on doing public benefit work. We do a lot of studies that we then publish on our website that are freely available for everyone. So that's just a quick snapshot of who we are. As Javier gave a great introduction, we've really seen a growing trend in open energy modeling, especially over, I'd say, the last 5 years. I think historically commercial tools were used extensively and mainly sitting kind of within government planning departments and utilities who would develop the different capacity expansion plans as well as sort of resource adequacy modeling right down to transient stability analysis. In the South African context, a lot of this capacity expansion planning has been historically done by the DMRE and Eskom for our integrated resource plan, and that's predominantly based on the commercial software Plexos, which is kind of the most widely used energy system planning commercial tool. One of the challenges that there is the sort of the commercial tools land up being a bit more black box in nature. So it's not so transparent in terms of all the modeling decisions that are made. And it's also the licensing costs are often prohibitive. So what happens is that it creates a barrier to entry, and you land up with only a few groups that have kind of limited license to commercial solvers, or commercial software, and then it's more difficult to build a kind of broader community of practice and getting more people interested and involved in energy planning. So I think with the transition and opportunities that many industrial customers are facing, there's a huge skills deficit in this space. So we work with a lot of industrial customers who are trying to build internal teams now to try understand their energy systems, how they plan these into the future, what risks and opportunities there are that lie ahead for them. So definitely a need to provide additional support to get more talent coming through, especially from universities and postgraduate students. So we are sort of following a trend in this space. So there's a lot of countries that are more progressed on this sort of open energy modeling journey. And I think it's a great resource to look at the OpenMod initiative. And that's mainly on the European Union side of things. And there's a lot of really valuable information and skill sets that get shared on that platform. It's not only about PyPSA, there's a range of different open source modeling tools there, and really a wealth of information and interaction. So we highly recommend having a look at that. So just to say that the open modeling framework, essentially, it's not just about open source code and data. It's really about the whole process. And in many senses, the tool is just a tool that you use to build and solve the equations. But really, the magic happens on the input data, processing that data, and then actually analyzing the results and generating some insights across a range of scenarios. So I think there have been some very positive moves happening in the South African space. There's definitely a lot more interest in collaboration between modeling groups, whether it's work that's sort of being done by the Energy Council, by ourselves, from UCT, Stellenbosch, and other universities across the country. And ultimately, I think as a community, it will really increase the rigor of the modeling work that we do. If we can start to develop, for example, a set of standardized test cases where we can start to benchmark our models against each other, I think that, and we can always go back and then check that changes to our code base are kind of relatively well aligned with kind of standard set of test cases. So definitely looking forward to engaging on that in the future and seeing if we can start this year to publish kind of an agreed set of input data assumptions, and then we can take those and we can all run them through different models, whether it's commercial models such as Plexos, or for example, some of the Saturn models, PyPSA. I know there's work being done on osmosis as well, for example, in South Africa. So there's quite a lot going on. Just in terms of the energy landscape in South Africa, I think we come back to just the importance that the kind of an active and independent energy modeling community has played over the recent years. And I think just highlighting some of the work done, especially by CSIR, ourselves in collaboration with CSIR, the UCT, ESRG, and others who've really helped to provide more open energy modeling and data into the public discourse. And really, I think it's played a significant role in supporting some of the discussions, for example, around the IRP as we move forward. So in terms of the PyPSA platform itself, so PyPSA can be thought of as it's a toolbox. And there's a range of different modules that you can take from that toolbox and then assemble to produce a power or energy system model. So it's not specifically only focused on capacity expansion planning, but that's kind of the area that we use it most for. But really, it can do anything from intertemporal optimization, so perfect foresight, multi-horizon planning. There's also modules that can then look at unit commitments and more resource adequacy modeling, more shorter dispatch rolling horizons, for example. And really, yeah, I think the code base itself has been improving quite significantly over the last couple of years. And you can see on the right-hand side just the sort of exponential growth and interest that's coming related to PyPSA. So these are some of the other tools as well, but really we've seen PyPSA as one of the kind of leading frameworks in this space. So we shared this at the previous open energy modeling workshop that we did, but I think it's useful to just provide a bit of an overview of how we've gone through this journey. So specifically when I started out, I knew absolutely nothing about Python. I came from a modeling and optimization background, predominantly working in MATLAB actually back in the day. But I think these days there's a huge wealth of resources, and I think the advent of AI models and ChatGPT can really help you come up the learning curve very quickly. Especially using Python, I think it's quite easy to use these large language models to either drop functions in that you're trying to understand, or if you can actually get it to code you different functions, or at least help you through that learning curve, which is very valuable. So you can get a bit lost in the world of going down thousands of Python, like more generic Python programming tutorials and videos and courses. But I think what's more useful is to keep it focused and rather start applying it to actual energy system problems rather than doing too many different parts of Python that you might not actually have to really use for your system modeling. So once you've got a kind of basic understanding of some of the core libraries with Python, so that would be really your NumPy, which allows you to do a lot of matrix algebra. PyPSA itself heavily relies on pandas and Xarray. So those are two great libraries to get into. And then just some of the basic plotting libraries from Matplotlib. I think once you've got a view of how to use those, that gives you a very good platform to then start to jump into actual PyPSA models. And you can start off with very simple networks that just help you learn the building blocks. So how do you assemble different generators to a network? How do you couple that with load? What are all the key inputs and outputs? How do you access those in the model, etc.? So once you've got that and learning the building blocks, then you can start to develop your own kind of in-house smaller toy models. Now you're starting to use the tool to solve some of your problems. And we went through this process. Actually, the kind of the first set of models we built were around load shedding and just a very simple dispatch model of the South African power system, which we found was actually incredibly accurate in terms of replicating how a system operator would dispatch a set of resources across the country. So that was kind of our first sort of delving deep into these in-house models. And then once we got to grips with that, we started then looking at the more complicated national power system models. So as a first step, the kind of level of complexity from going from a smaller toy model where you can run it really in a sort of small Jupyter notebook to now a bit more of a complex model. There's a lot more input and output data. and you often have to get a workflow management tool that will allow you to process all of this information, run these scripts, and then look at the output. So that was kind of the first step up that we had from going from smaller models to a bit more of a bigger, more complex model. And then along the way, once you start to build proficiency in the code base itself, you start to learn and identify areas where, hey, maybe there's a feature that's missing, or you've thought of a clever way to approach some kind of functionality within the code. And then you can start to actually make changes to the code base itself, and contribute that back to the community. So, for example, we have some functionality that now actually sits in the PyPSA library, which was developed by ourselves, and then we contributed that through different pull requests to PyPSA. So, just in terms of a snapshot of kind of the different types of models that you can build in this space. So really, if you're looking at the kind of long-term capacity expansion planning, so historically in Plexos, that would be called like the LT plan. And that's really about figuring out what investments you're going to make in the long term. And then you start to move down to production cost or resource adequacy modeling, where you're saying for a set of generation resources, how can these best work together to match supply and demand at least cost? And then you can start to do different forms of power flow modeling. So PyPSA does have some ability to do right up to sort of linearized power flow modeling studies, and you can do, there is some functionality around nonlinear power flow modeling. That's not really something that we have dived into detail with. So we've been sitting mainly in these first two blocks around capacity expansion planning and production cost modeling. And transient stability is something that I don't think that is available in the PyPSA platform. So what is a capacity expansion model, and what are the different types of inputs and outputs that go into this? And really, if we look at the problem that's trying to be solved, you're trying to minimize the sum of investments in new generation as well as marginal costs of existing generation to essentially find this minimum point or point of least cost. So in terms of inputs, you have demand inputs. So that's typically hourly profiles and how that's projected to grow over time. Then you might have an existing fleet of generators. So in our case, the existing ESCOM fleet, as well as REAP generators, what's happening on solar PV, rooftop, etc., as well as the REAP. And essentially there you're trying to capture all the technical characteristics of those generators. So if it's conventional generators, things like ramp rates, heat rates, emissions intensity. For your variable renewables, it's about hourly supply, profiles, etc. And then you have new build generation and storage technology options, where there you're looking at specifically what are the costs for those, the costs and supply characteristics for those technologies, and again, how those are going to change over time. So a lot of techno-economic data that has to be collected across all these generators. And we've spent a lot of time trying to take information from different sources, whether it's from AMO or NREL, or so just benchmarking a range of new technology cost options, and we've made that available on our website. So there's a pretty extensive Excel workbook that can basically be seen how different organizations are projecting how these costs are going to change over time. Then within your optimization, there are different constraints that can be applied. So the first fundamental constraint is that you're trying to really match supply and demand, although there is some level of load shedding that you can allow in the model for a limited number of hours, so you don't avoid cases where you overbuild for just a few hours. And then some of the more common constraints that you would apply are emissions limits, and then new build constraints. So specifically because of grid limitations, how much new technology you can build where. The final constraint that we've started building into our models is a bit more realistic contracting around gas. So historically, a lot of models would allow gas to be used as a peaking fuel. So there's a lot of OCGT capacity that's fired by gas, but really running at very low capacity factors. So when you speak to people in the gas industry, they say from kind of a contracting and infrastructure perspective, that gets really challenging. So what we've started to do in our models is build in minimum monthly offtake if you want to use gas at a certain price. Otherwise, you have to use higher price gas or liquid fuels for that peaking role. So essentially what happens is that all this input data gets translated to a set of linear equations. So there is a possibility to do some quadratic constraints. So for example, if you had an efficiency curve that changes with power output, or how your marginal cost changes depending on different levels of output, that is possible, but it does increase the computational load quite significantly. And these are already fairly large models that take significant computing resources to solve. So typically in our space, we stay in the linear world, and we've got a set of linear equations that then need to be solved. So although we're talking about fully open source energy system modeling, at this point, it's important to work out that what PyPSA does is just really assemble all the mathematical equations that they need to be solved. And it's important to note that there are open source, or what we would call solvers, that are available, where essentially you can it's completely freely available, and it will help you solve those mathematical equations. But the reason that commercial solvers exist is because there are teams of PhDs working on them, and they are just far more efficient in terms of solving problems. So the open source solvers will, unfortunately, at this point, only really solve small problem sizes. If you want to do sort of more significant problems, especially that involve sort of perfect foresight with full chronology, so you're solving every hour in the year over multiple decades, then you typically have to make an investment in a commercial solver. So if you're a university student or academic, I believe you have free access to pretty much one of the best commercial solvers, which is Gurobi. So that's great. And then in terms of the more commercial space, there's options for Gurobi. We currently use Express, and Cplex as an option. And there's also some new solvers that are coming out from the Chinese market at the moment. So MindOpt and COpt are some sort of, actually the performance on linear models is starting to increase substantially from those models, and they are often a lot more cost effective than the traditional commercial solvers. So essentially, we take all the input data, we convert that to a set of linear equations that gets then sent to a solver that then works out the maths and solves the answer of all those simultaneous equations. And then PyPSA will take that result and post-process it back into useful information. So part of the kind of outputs that you get then from the model are what the optimal investments are that you made over time, how the energy mix will change between different technologies, what capacity is being added or removed from the system, and then the actual hourly dispatch of each of those generation assets, what load shedding there is, if any, and a more sort of a very hot topic at the moment around curtailment, and where there's likely to be areas of significant excess generation in the system. You also get a lot of information around costs, so total system cost of what you've modeled, and then investment and operational costs, as well as sort of an average tariff path. So there's not a 100% direct connection between what these capacity expansion models will say the average tariff path is, and that means that's going to be the ESCOM tariff. But it does help show you kind of what the trends look like, and is that path kind of stable in real terms, or is it actually likely to increase over time, or how is the energy system dynamics changing? Then kind of the final main category of outputs that's becoming increasingly important is around emissions. And there you can start to look at what the average grid emissions factor would be for each mix, and how our overall emissions will sort of come down over time. So for the single node model, which doesn't include a co-optimization of kind of the main transmission corridors, the costs are really for generation and demand that are co-located at a single node. But so those transmission costs are not included in those models at the moment, which are estimated kind of in the 10 to 15% range. But as we start to work to more spatially resolved models, it starts to give you a little bit more insight in terms of what transmission is required between different regions, and also you can make some estimates around the cost involved for that. So just to kind of highlight two recent publications that we've released related to open energy modeling. I think the first is the data set that I was speaking about around a kind of comparative cost analysis, and really looking at what all these different institutions are making in terms of projections, whether it's predominantly most of the projections are for renewable-based technologies, but there are some projections as well for conventional generators that are more mature. So that's a very valuable resource. If anyone wants the workbook, you can download that off our website. It's freely available, and it gives all the input assumptions, everything that we could find from every source. We've kind of lumped those together, and you can use that to then kind of develop your own projections in terms of different costs. The second recent publication that we've done using our own open source energy model, PyPSA-RSA, was for our kind of comments that we made around the recent IRP draft that came out, and that study is also available on our website. And we've included all those scenarios as well in the GitHub repository for PyPSA-RSA. So if you want to take those scenarios and start to play around with them yourselves, once you're up to speed with the PyPSA-RSA model, all of that modeling that was set up is now freely available. So as I said, just an interesting place to start for this. Was one of the very first models that we built in PyPSA, and it's just a single node dispatch model where we lumped every technology category together at the level of data that's provided in the ESCOM data portal. And then we had different constraints around how the pumped hydro, as well as the kind of diesel refueling to the OCGTs was based. And this is a really fun model to put together and then try work out how well your version of the dispatch matches what actually happened in the system. So I highly recommend if you're looking for an interesting toy model to start off with, you can use the ESCOM data portal info to get how, for example, there's availability of different generators, and then you can build that model in Python and PyPSA and see then how it responds if you were to change things in the system. So we use this a lot to, for example, look at if we'd had an additional 5 gigs of solar PV and wind in the system, what effect would that have had on load shedding? And from this, we really got a lot of interesting insights, which were almost counterintuitive to a lot of stakeholders at the time, and just showing how can adding variable renewables into a system that is so energy constrained, what a significant difference that makes in terms of the operation of the overall fleet and the different assets, and that having more energy from any source allows you to keep more water in your pump storage dams and keep more diesel in your diesel tanks, and then you can dispatch that in other hours. So this significant effect that it has in improving system stability and adding more load shedding resilience. In terms of just where different planning studies are envisaging the energy mix in terms of installed capacity from different renewable and dispatchable technologies, we see there's a growing body of studies that have been done. So we have the RP type studies, what's ESCOM has put forward in the TDP. Then we have a range of scenarios that we've modeled previously for our ambitions work, which was back in 2020, and then our more recent work. And those scenarios cover a range of different outcomes, whether it's kind of a least cost unconstrained expansion or more constrained renewables build out, and different carbon constraints in the system. And then there's work also that's been done for PCC, the SATIM model, and for example, for the World Bank CCDR study, I believe that was based on the SATIM model. So what you'll typically see in the output results is that our more recent studies are a bit more solar PV heavy in the mix, and that's predominantly driven by the constraints that we applied to the model. So in our recent work, we really viewed solar PV and battery storage as the quickest way to address. Oh, sorry, my computer seems to have just. The quickest way to address the energy crisis and really getting new capacity into the system as quick as possible, whereas we had more moderate constraints on the rate that wind can be built at in the short to medium term. So at the moment, a strong focus on electricity and power system modeling, but this is really, I think, ultimately a first step in the types of models that are going to be required into the future. And this concept of sector coupling and how we can start to increase the flexibility of our electricity system to handle more and more variability from solar PV and wind. So if we look in the electricity sector alone as it currently is, really the main opportunity to provide flexibility is going to come through different energy storage devices, whether it's from batteries, compressed air, capacitors, flywheels, and pumped hydros, obviously the main storage device used on the network at the moment. But in the future, what we start to see is as the cost of energy from variable renewables continues to be driven down, this creates new opportunities to start to decarbonize other sectors of the economy that are produce emissions. And really those are sort of around mainly mobility and process heat. So as we start to get these opportunities to electrify, for example, heat demand, this creates new opportunities to couple that with different forms of energy storage. So, for example, thermal energy storage might come in an order of magnitude cheaper than battery storage. So what happens is once you electrify a certain heat demand, you can couple that with thermal storage, and this now starts to provide the flexibility that you need in terms of variable generation from renewables. On the electric mobility side, different forms of electrification of transport, but really how you can start to use flexibility in EV charging around sort of, again, adding flexibility into your overall energy system. And then sort of hydrogen as an intermediate fuel carrier that has then opportunities in mobility, as well as sort of different green chemicals and green liquid fuels, for example. So what we see already happening internationally, and there's some great examples of this using PyPSA, is starting to build sector-coupled models that include these other end uses of energy and showing some of the flexibility that you can get in terms of what that means. Sorry, just one sec. What that means to the energy sector. So there's a model called PyPSA Europe sector coupled, and that's a fully integrated model of the European power system, plus the gas networks, building heat demand, process heat demand. It's quite a significant and complex model, but really tries to capture now this fully integrated system. In terms of the local context, we believe Fraunhofer has started doing some sector coupling work with Agora, and we're hoping that some of that model code, or some of the code from that model will be transferred to the PyPSA-RSA base. So we'll have that soon.